Here let us talk about this one bar under axial tension or compression. This is the axial tension or case. The bar is straight and features a uniform cross section. Here you can see this. If I take the cross section, that will be uniform and is composed of homogeneous material. Okay. In compression, it is either short or constrained to prevent lateral buckling. Okay. Loads are applied centrally at the both ends. Here you can see centrally we are applying at both ends to maintain uniform stress distribution across the cross section, ensuring that the stress remains within the proportional limit. This also you can see it. Behavior, if you see this, when subject to tension, the bar elongates. Under compression, it shortens. The unit longitudinal strain is denoted SE. The total longitudinal deflection is del D. Here you can see this is the longitudinal deflection as D. You can see it. And perpendicular to the applied load, the bar contracts under tension and expands under compression. If you see in the lateral direction, it can contract, right? It can contract if it is tension is applied, and it will expand under compression. That with that unit lateral strain E naught, beginning being uniform in all transverse directions. If you see, this is the transverse direction. If the cross sectional area, because of this tensile load, this will get compression, right? This will contract. Suppose if I apply this as a compression, then it will try to expand. I'm talking about in the cross transverse direction. If you take the cross section here, if you apply this load in tension, these lateral directions, it will contract. So the lateral deflection D naught from original to here, D naught in any direction is proportional to the lateral dimensions D measured in the direction. Both longitudinal and lateral strains are proportional to the applied load. Uniform tensile compressive stress, yes, exists on any cross section, while an oblique section, here if you take an oblique section, there are uniform tensile compressive normal stress and shear stress. This sigma naught is the right, that's nothing but it's equivalent to Sy, and then this tau v, tau y, that's equivalent to tau theta. So P is the applied load and A is the cross-sectional area before loading. L is original length before loading, E is Young's modulus of elasticity, and N is the Poisson ratio. Here you can see this, the P is the applied load. Sigma is the stress. Tau theta is the shear stress on the oblique plane. Sigma theta is the shear normal stress on the oblique plane. Here we can see this graph unit stress. Unit stress is equal to P by A. Here we are talking about this sigma is nothing, but here you can see this sigma is P by A. Same way I'm talking about S also, we can put it S equal to P by A, that is a unit stress. And then here sigma theta, it's a P by A cos square theta. Here you can see this sigma theta is the right. This is nothing but it's equivalent to Sy in the oblique normal stress in the oblique plane, that is P by A cos squared Y. P by A cos squared theta. Y means here I'm talking about like this is the theta value. I'm talking theta is equivalent to Y. I'm taking it in this formula. Sigma is equivalent to S, just for clarity or simplification. And maximum Sy is happens when theta equals 0. When this theta equals 0, that means this value Sy means is on the oblique plane, right? This oblique plane, the stress will be equivalent to S, that's the maximum when Y equals 0. Theta, if it is 0, this plane will become this, right? This is the plane. I can say that this theta is there, right? This is the plane. If this plane theta is 0 means it will come like this. So in that plane sigma will be the maximum stress, that is nothing but S, that is P by A. So because theta equals 0 means cos squared theta is 0, so P by A maximum it will come. And shear stress equal to tau equal to P by 2A sin squared Y, that is this tau theta. This tau theta we are taking P by 2A into sin 2 theta. The maximum it can happen tau theta equal to 1 by 2 into sigma, half of sigma. Maximum it can come half of sigma only, it can come, that is theta 45 degree and 135 degree it's coming. That means here you can see maximum this tau this shear stress is right, that will be, it can be equivalent to S. So max tau y equal to 1 by S by 2. That's a maximum S. Normal stress, half of that it can come as a shear stress. Longitudinal strain, that stress S by Young's modulus, that's a longitudinal strain. Longitudinal deformation, you can see this LE, that's length L, E is a strain. So longitudinal deformation maximum can come PL by AE, that's a longitudinal deformation. Here you can see this longitudinal deformation, original length into strain, that is the longitudinal deformation, and transverse strain is minus Poisson ratio into longitudinal strain, that is here. Lateral strain is Poisson ratio into longitudinal strain, E is longitudinal strain. Total lateral deformation is T dot into lateral dimension changes lateral strain into lateral dimension. So lateral strain into lateral dimension. And strain energy per unit volume is 1 by 2 half of stress squared in divided by Young's modulus. Strain energy per unit volume half into stress squared by strain, and total energy means total volume you have to include. This is per unit volume. Total volume is L is the total volume. That's equivalent to half into stress load into displacement. That's exactly here also. Unit strain is means half of stress squared by Young's modulus. Total strain means half of unit strain into volume. So that will be equivalent to half into load into distance. That is the total strain energy. Okay, Walid. I will make one simple example, then you can understand. Here we will see the example. Consider the example cylindrical rod that is 4 inches long. So this is the cylindrical rod. It's a 4-inch long, and the diameter is 1.5 inch. Diameter is 1.5 inch. Okay, subjected to an axial compressive load. Compressive load means you will add like this. So 2000 pounds axial compressive load, and Poisson ratio 0.285, Young's modulus 30,000 pounds per square. So what we are going to compressive stress we will calculate, and longitudinal deformation we will calculate, transverse deformation, change in volume, and the total energy work done also. So stress we can see S equal to P by A. P is the load, that is 20,000 pounds. A is the cross-sectional area, so we can get this one. And this strain we can calculate. The strain means longitudinal strain. We know stress by longitudinal stress by Young's modulus. That's the strain. So S by E we can calculate. S is we calculate here, and Young's modulus we know. So and deformation, if we see, deformation is nothing but original strain is what? Original length. Change in length by original length, right? So deformation we can calculate D. D is a deformation, right? Deformation we can calculate based on the strain and original length. So if you multiply the strain and original length, you can calculate the deformation. Actually, it is shortening because of compression. It is shortening. And lateral strain we can calculate. Lateral strain is what? E naught equal to Poisson ratio into longitudinal strain. Lateral strain equal to Poisson ratio into longitudinal strain. We can calculate. And D naught is the lateral change in dimension, right? D naught equal to lateral strain into lateral dimension. Longitudinal dimension we put it here, right? The same way lateral strain into lateral dimension. So we can calculate the lateral dimension also. So longitudinal dimension also we can see. The original volume is we know half in pi into A squared into length, right? And the change in volume is half into NE into V. NE is the lateral one. E is the strain 0.0037, and this is the volume, original volume. So half into Poisson ratio into strain into length approximated, because change in volume can be approximated, minus 0.004. This is how we can approximate, and we can see the increase in strain energy. We can see strain energy is half into force into displacement, whatever the displacement. Displacement is the, here we have seen longitudinal displacement 0.000159, and force we know, and this is the total strain energy. Here today we will talk about discussion. All right, everyone, we can let's dive deeper into the formulas we use for axial tension compression. I think understanding these can clarify how we approach engineering applications. Okay, great idea, Ram. The first formula we often look at it is the unit stress S equal to P by A. It's so straightforward, right? But it lays groundwork for the everything that follows. See, understanding how load P and cross-sectional area are related to its fundamental. And when we increase the load or decrease the area, if we increase the load, S is proportional to load. So if we increase the load or reduce the cross-sectional area, we can quickly see how the stress increases, right? This is why it is critical to design components with sufficient cross-sectional areas. If components doesn't have the sufficient cross-sectional areas, it's a problem. So especially in high stress applications, we should have sufficient cross-sectional areas. That's the key point. The once we have the stress, then we can move on to calculate. We move to calculate strain. So once we have the stress, we move to calculate the strain using S strain equal to stress by Young's modulus. The modulus of elasticity you see here E, that helps us understand how much deformation we can expect. So if the Young's modulus is more, then this strain is less. So we can understand the E helps us understand how much deformation we can expect. It's fascinating how different materials have vastly different elastomodally influence their applications, right? Exactly. The strain formula that allows us to relate stress to deformation directly. It's crucial for engineers to remember that this relationship is only holds within the elastic range. Beyond that, we need to consider some more complex models. And don't forget that the lateral strain, that E naught is the lateral strain. That's nothing but multiplication of Poisson ratio into longitudinal strain. You know that this Poisson ratio gives us insights into how materials behave in multiple dimensions under load. This is especially important in applications where lateral support is a concern, right? And when we calculate the total transverse deformation, D naught is the transverse deformation, so we know the transverse lateral strain into transverse dimensions. Then we can get the transverse deformation. It shows how interconnected these strains are. It's fascinating how applying tension in one direction applies affects dimension perpendicular directions. So if you apply tension in one direction, it affects really the dimensions in perpendicular directions. So speaking of which, let's discuss change in volume. We can calculate the volume change equal to half into strain Poisson ratio into longitudinal strain into volume. It's interesting to see how lateral dimensions deformations can lead to overall volume changes. It can be critical in tightly constrained systems. Volume change can affect fluid dynamics in pipes and even the behavior of soils in geotechnical applications. Understanding how to calculate this change is vital for effective design, right? And don't forget that the strain energy formulas, total strain energy, you can calculate U equal to half into force into displacement. That gives a direct measure of work done on the material. This is crucial for assessing how much a load a structure can withstand safely bear without risk of failure. That's a great point. The energy stored in the material not only indicates how much load it can handle, but also how it can respond to dynamic loads. That's particularly important in seismic and designs and all. Each of these formulas offer a different perspective of behavior of materials under load. Understanding how these interrelate, that helps engineers to make informed decisions in design analysis. So to summarize, we have covered a fundamental formula for stress strain and lateral strain, volume change and strain energy. So each plays a crucial role in understanding the material behavior, and collectively they inform our design processes. It is important for all of us to be comfortable using these formulas. They form the backbone of much of our engineering work, and being able to manipulate with them confidence can lead to better designs.